Hello everyone, welcome to my talk. I am Maciej Pacut from University of Vienna. Today I'm going to present my paper titled Optimal Algorithm for Online Multiple Knapsack. This is joint work with Marcin, Bienkowski and Krzysztof Piecuch from University of Wrocław. In the knapsack problem, we are given a container called knapsack and a bunch of items. The goal is to select which items should we pack into the knapsack and which items should we leave out. I'll give a formal definition of the problem in a second. We consider the problem variant called the multiple knapsack, where we manage a number of knapsacks. In this problem, we have a fixed number of knapsacks. Don't confuse it with the bean packing problem, where the number of beans can grow. Let's start from a familiar definition of a textbook knapsack problem, and let's introduce the online multiple knapsack by pointing out the differences. In the algorithms course, the classic knapsack problem is used to illustrate dynamic programming. It is formulated as follows. We are given one knapsack of capacity 1 and a set of items defined by their size and weight. The goal is to choose the best subset of items to pack into the knapsack without violating its capacity. This problem is offline, which means that we are given the entire set of items at the beginning. Given the set of items, we can access them in any order we like. For example, compare items or sort them. During this talk, we consider a simpler variant, where the weight of each item is equal to its size. The capacity of knapsack is still 1, but now we maximize the total size of accepted items. Don't confuse this problem with fractional knapsack, where we can take fractions of items. This would be trivial, however in the knapsack problem we have a 0-1 decision to take the entire item or not. In the multiple knapsack problem, we manage n knapsacks, each of capacity 1. For each item, we not only decide to accept it or reject it, but additionally we assign accepted item to a knapsack. While assigning items, we must obey the capacities of each knapsack. The goal is to maximize the total size of accepted items by summing up the items from all knapsacks. The changes described so far are minor in comparison to the last change. We consider online knapsack. In contrast to the offline version, now we no longer have access to all items at once. All we see is the current item. The sequence of items arrive one by one. Upon seeing an item, we either reject it or store it in one of our knapsacks. We emphasize that the decision must be made without the knowledge of future items. Moreover, the decisions are permanent, so we cannot, for example, move accepted items between knapsacks or reject a previously accepted item. Our goal is to maximize the total size of accepted items. To measure how well we did, now we compare ourselves to the optimal offline algorithm that sees the entire sequence of items in advance. In online algorithms, this is called a competitive ratio. To sum up the model, we consider an online proportional multiple knapsack, and the goal is to maximize the competitive ratio. Prior to this work, the best known algorithm was half-competitive first-fit algorithm. The half-competitiveness means that the algorithm accepts at least half as much as the optimal offline algorithm. The analysis of first-fit holds as long as there are at least 2 knapsacks. The other known result concerns the case of one knapsack. In such scenario, no algorithm is competitive. Consider a sequence of 2 items, a very small one and a large one. If we reject the small item, the adversary ends the sequence without giving the large item, and our gain is 0. The optimal strategy is to take the only item in the input. On the other hand, if we accept the first item, then the optimal algorithm waits for the larger one and accepts only this one. We cannot fit the second item due to capacity constraints of our knapsack. This example is the rationality behind studying multiple knapsacks. More negative examples exist in the literature. For example, multiple knapsack with weighted items is non-competitive, even in the randomized setting. Known results for online multiple knapsack are the following. We already mentioned the first fit algorithm, and in the same TOCS 2016 paper, Zygan and others provided an upper bound of approximately 0.59 for the competitive ratio of any randomized algorithm. Prior to our paper, these results were best. We provide an improved deterministic algorithm for the problem called the rising threshold algorithm. This algorithm is optimal in a sense that its competitive ratio matches the randomized upper bound. Now we describe the rising threshold algorithm. The name will be clear shortly. The algorithm classifies items based on their size. For example, we said that items of size at least half are large. At most, one large item can fit in one knapsack. Later we will define medium and small items. As a warm-up, we define the rising threshold algorithm for large items only, and we show it is optimal. The plan is to later extend the algorithm for medium items and then for small items. Given a number of knapsacks, even before we see the first item, we assign a threshold value for each knapsack. Upon seeing an item, we attempt to put it into the leftmost empty knapsack, and no other knapsacks are considered. Precisely, we compare the size of the item with the threshold of the knapsack, and we accept the item if it is larger or equal to the threshold, and otherwise we reject it. Now we describe how to assign thresholds to knapsacks. We wish to handle all possible number of knapsacks. To this end, we construct the thresholds with the help of a continuous function f, with the formula given on the slide. We justify the choice of f later. To assign thresholds to knapsacks, we draw knapsacks next to each other in 1x1 square. And we use the plot of f to determine the threshold. Precisely for the ith knapsack, we assign the threshold f of an argument 1 divided by I plus 1. We have chosen the function f for its unique properties. For example, its value starts to rise from the argument 0.59. To see how we can use it, consider a sequence of n large items that are just slightly larger than half. We accept these items until we fill 0.59 of our knapsacks, and we accept no further knapsacks as they don't meet the threshold. In comparison, opt accepts all items in the input sequence, and we are 0.59 competitive. F is the only function that generalizes this property. Assume that the input sequence consists of items smaller than the blue line in the figure. Then, opt is at most the area below this line. On the other hand, the items accepted by the algorithm satisfy the thresholds, and our gain is at least the integral of f. The ratio of green area to blue area is exactly the desired competitive ratio. This holds for each value of f. We use this property to show the optimality of the rising threshold algorithm. It suffices to combine the aforementioned property with the following observation. If an accepted item was strictly larger than the threshold, then it benefits both alg and opt. This suffices to conclude that the rising threshold algorithm is optimal for large items. Next, we show what the algorithm does when it encounters a medium item. These items are larger than 1/3, and at most 2 medium items fit in one knapsack. For now, let's briefly sketch some properties of the algorithm. We will provide the details later. We still treat large items according to the threshold. Namely, f large item must be at least f of the argument 1 divided by I plus 1. Also, we never reject a medium item, except when we run out of knapsacks, at which point we terminate. These properties alone allow for a powerful observation. Namely, if the input sequence ended while we still had empty knapsacks, then we are optimal. The analysis follows using the same arguments as in the analysis for large items, given that medium items benefit both alg and opt. This observation allows us to focus on cases with no empty knapsacks. We still have a lot of flexibility in designing the algorithm as long as we satisfy these properties. Consider the case where the algorithm finishes with no empty knapsacks left. When we run out of knapsacks, we terminate. Then the adversary might inject n items of size 1, and all of them are accepted by opt. This significantly simplifies the analysis, as now we are no longer concerned with the competitive ratio. Instead, we just focus on maximizing the gain of the algorithm and showing that it is at least 0.59. We accept each medium item, and the only decision is how to arrange them. The first option is to combine a medium item with a large item. This guarantees us the largest gain of available options. However, this is not always possible, as they must fit in one knapsack. The second option is to place medium items one per knapsack, with hopes for combining them with large items that arrive later. The third option is to stack two medium items together in one knapsack. Given these three options, the rising threshold algorithm arranges medium items in the following way. It always attempts to combine large and medium items, regardless which one comes first. If it's not possible to combine, we keep some number of medium items waiting. If too many items wait, we start stacking them together. We must strike a perfect balance of waiting medium items. It is easy to see why we shouldn't keep too many medium items waiting. However, we can have not enough waiting items too. Consider the case where all waiting items were combined with large items. For example, in the figure on the right, all 5 medium items arrive before large items. Notice that the items that are now combined are precisely the items that were waiting prior to arrival of large items. Recall that gain of the algorithm must be equivalent to the area under entire function f. However, stacked medium items contribute much less gain than the threshold value. The part that is missing is depicted by the green dashed area. The missing part must be compensated by waiting items. I hope I convince you that we must strike a perfect balance with the number of waiting items. To determine how many items should wait, we first consider a simpler scenario where all medium items are the same size, and we generalize it later. So how many medium items should wait? Let's give a simple yet generic answer for this question. The right amount of waiting items should give us the gain 0.59. Let's inspect the gain of the algorithm for a given m. Waiting items are size m. Stacked items are size 2m. Moreover, waiting items contribute to gain on large items even if they are not directly combined with them. Recall that we always attempt to combine medium and large items. Hence, if some medium items wait, then large items were big enough so they were never combined. Precisely, the gain on each large item is both larger than 1 minus m and larger than the threshold of its knapsack. In the paper, we present the formula for the number of items that should wait. To obtain the formula, we fix m. We use the number of waiting items as a parameter, and we solve for the desired gain 0.59. This gives us the optimal algorithm for large items and a single medium item. And we want more than that. The tricky part is to generalize for various sizes of medium items. If we look at this curve again, we see that the answer for each value of m is different. This seems like a set of contradicting constraints. So see how we did it. First, sort waiting medium items. Then, draw the curve for single medium items of size m. Our criteria is the following. We decide that the medium item can wait if it fits below the curve. A careful analysis of this criteria shows that it indeed works. The most important values used in the analysis are the medium waiting item depicted red and the items that touch the curve depicted green. We analyze the raising threshold algorithm in terms of these values. It is possible to extend this strategy beyond 1/3. We keep all waiting items below the curve together. When we are stacking the items that did not fit under the curve, we try to combine similar items together. Notice that now we can stack 3 or even 4 items together. We hit the limit at alpha, where we can no longer provide sufficient gain in all cases. Finally, we sketch what the rising algorithm does for small items. Similarly to medium items, we never reject a small item for exactly the same benefits. The medium approach does not work for small items, and new ideas are needed. We emphasize that simply stacking these items is not enough to obtain the desired gain. To give you a taste of the ideas we use to solve the problem of small items, we consider the fourth option besides combining waiting and stacking. This fourth option is to merge a number of small items into a medium item. To this end, we stack them until they reach alpha and then merge them into a medium item. Note that this merged item is not exactly equivalent to an incoming medium item. For example, we cannot assign it to any knapsack, and it must reside in the knapsack where it was merged. I just barely scratched the surface. To see the details, I recommend you to read the paper. To sum things up, we designed the rising threshold algorithm using a function that is natural for this problem. Our solution, the rising threshold algorithm, is optimal for online multiple knapsack problem. This result was presented by Maciej from University of Vienna.